Everyone. Hope everybody's doing well. I had uploaded the assignment one on mass volume relationships. Are there any problems with it? The solution sheet is up there. It's pretty straightforward. If you know the basics, it's pretty straightforward. However, if you have any issues or any concerns, by all means, get in touch with me, okay? And we can review it. It gives you a background to the point that when we do mixed designs, you'll understand how specific gravity, the aggregates, are going to be used to determine volumes. When we get into mixed designs, there's different ways of doing it, okay? You can actually do it from previous test data, run a statistical analysis on it, and if previous test data for that mixed design that you want to use is good, you can go ahead and use it. The most common one is the absolute volume, and that's the one we're going to be working with. And again, that's where the specific gravity comes in, because you can use a specific gravity to determine the density. And when we work on volume and density, then you can back calculate it and get the mass. Mixed designs and concrete batching is mostly done by mass, which is more control oriented instead of by volume. So we design in volume, but we're going to back calculate it and get all our batch weights in mass, okay? So we'll look into that a little bit more when we get into the mixed designs. I've uploaded this unit. It's a PowerPoint presentation, and I have one that's uploaded with audio. The one that's uploaded, there's an audio with every slide. So when you're going slide by slide, I have made up a little audio about the content of the slide. You're going to have to download it first from Learn to be able to, I believe, to trigger the audio. So if you're having any issues or any problems with it, let me know. But typically PowerPoints, when we're in the classroom, I basically talk about the PowerPoints. But here, I actually played around with it and put an audio to each slide. So there's a lot there. I'm going to go through it quickly. I'm not going to go through in great detail for the simple reason that there's already an audio on every slide. Don't get panicky. There's something like 80 slides. A lot of it is information that is required on your behalf, but you don't have to have it or know it for an exam or a quiz. It's information that ties things together. Like I mentioned in the last class, there's a lot of theory in this course. When we're talking about aggregates, we're going to be talking about cements. We're going to be talking about mixing water. We're going to be talking about admixtures. We're going to be talking about supplementary cementing materials. Some of you that have worked in concrete understand that there's fly ash that's used, there's silica fume that's used, there's natural pozzolans that can be used to work with the cement and give us better properties. Okay, so there's a fair amount there, and like I mentioned, if you work in the industry, you eventually acquire that information. Any questions so far? Okay, what I'm going to do is I'm going to bring up the PowerPoint. The one I have here, the one I'm going to be showing here doesn't have the audio because I'm going to be thumbing through it, and I'll be talking a little bit about it. But there's more detail on the audio. So again, like I mentioned, if you're having any problems with it later on, let me know. So I'm going to bring that one up, and we can go from there. Okay, everybody can see this one? Yeah, okay, I'm going to go to a different screen here first. I'll bring my chat down here so I can see who's. Okay, it's not letting me. It's not letting me do the slideshow for some reason. Oh, here it is. Okay. Okay, aggregates for concrete. Okay, that's the biggest component of a concrete mix. And just on this little slide here, you can see where we've separated the aggregates into various sizes. And you've already done sieve analysis last year, so you understand the grading. For concrete, you need aggregates that are well graded. And when we look at concrete aggregates, we look at the coarse separately, and then we look at the fine separately. Because later on, this lab that you're going to be doing today is going to be more of a number crunching lab. You would actually be doing analysis and calculations. We're going to mix concrete, or we're going to design a concrete mix for the City of Winnipeg specifications. Some of you may have worked with the City of Winnipeg and have tested the concrete that is being used in city projects. Well, those mix designs had to be made by the supplier, and then they had to get approved. So they look at their aggregates and they look at all their individual ingredients. So the City of Winnipeg specification, which is also uploaded into Lab 2, CW 3310 R17, that's their latest specification. And you'll see that there's a link to the City of Winnipeg standard construction specifications. When you go to that link, you're going to be able to download that spec, and it's under Surface Works, and it's pertaining to the concrete pavement. Later on, we'll be looking, I believe, at 3310, which is the asphalt specification. So for now, we're going to be looking in the next lab in the next hour. We're going to quickly look at the City of Winnipeg specification, because we have to find the parameters that we're going to be designing for. The slump, the air criteria, the strength criteria the City of Winnipeg requires for their concrete. But anyhow, aggregates, key. If your aggregates are no good, your concrete mix is no good. That is the key. If you've got good, selected, processed aggregates, meeting grading specifications, durability requirements, okay, porosity requirements, you'll be able to mix good concrete. That's key. Okay? Okay, I gotta use my other button here. Okay. Sand, less than 5 millimeters. Okay? Typically, most of it passes the 5 millimeters. You need 100% passing 10 millimeters. And this makes up about 35 to 45% of the total aggregate. Okay, not the mix, but the total aggregate. You always want more coarse aggregate in your mix than you do fine aggregate. And when we batch separately, because you got better control that way. You can adjust your mix. Many times in rural areas, remote areas, you may have just pit run. In other words, the coarse and the fine aggregate are already mixed. And you have to have an idea of what is the percentage of coarse versus fine. And sometimes you can make adjustments in the field, sometimes you can't. Okay? But here, the suppliers locally, they have separate bins and they load their aggregates separately. Typically, they've got a coarse bin and a fine bin. A few years back, they wanted a 3-bin mix. In other words, 2 coarse and 1 fine. You had better control. You could blend the 2 coarse together to meet grading specs. And we're going to look at grading specs, and you understand all about grading specs from last year with Natalie. We're going to be looking at the grading spec for the coarse aggregate. We're going to be looking at the grading spec for the fine aggregate. And again, these specifications are CSA A23.1. Okay, remember, 0.1 are the specs, 0.2 are the test methods. Okay, so a lot of times you'll see something specified under A23.1 because it's pertaining to a specification, not a test procedure. Okay, coarse aggregates. Typically, we have them in size ranges. City of Winnipeg, 20 millimeters. Maximum nominal size, 20 millimeters. Okay, now, you heard me say the word nominal maximum size. Who can tell me what nominal maximum size is as compared to maximum size? You may have had that last year in your sieve analysis with Natalie. I'm not sure. Anybody? What's the difference? You heard me say maximum, nominal maximum size. Anybody got an idea? Blurt it out if you do. No? Okay, we'll come up to it. Here you can see two types of aggregates. You have polished aggregates on the right, and you've got crushed aggregates. Sorry, that was on the left, and you got crushed, rough textured aggregates on the right. Two different types of aggregate. Both, believe it or not, are acceptable in concrete, and we're going to get into that a little bit more. Okay, so these are rounded, cubical in shape. These are sharp and angular. These on the right, the sharp and angular, the crushed stone, you're going to find out that these would be ideal for asphalt, because asphalt works on interlock. Concrete works on a coating. Every particle has to be coated with a cement paste. Cement paste being fines, the real fine part of the aggregate, plus the cement, plus the water creates a paste. That's what gives you the strength, is the bond between these surfaces and the cement paste. With asphalt, you got to have some degree of coating, but the stability of an asphalt mix is determined from the interlocking of the aggregates. Anyhow, coarse aggregate. Again, I'm going to go through these quickly. There's different types. You know, there's igneous, metamorphic, and sedimentary. Our aggregates here locally in Winnipeg are typically sedimentary with some igneous. If you go to Stonewall, the aggregates that we looked at last week, remember I said they were crushed limestone. That's what we have in Carsey. It's donated to us. It's donated by Lafarge, and they typically donate crushed limestone from their Stonewall quarries, 100% crushed. City of Winnipeg, I believe, will not allow 100% crushed, whereas MI will allow 100% crushed for concrete. They're both acceptable. They're both doable. They just all have different physical properties. It's going to affect the performance of the mix. More from a workability criteria because of the rough texture. Again, different minerals. I'm going to go through this. Igneous rocks. These are various types. Basalt, one of the most dense, hard aggregates. Granite, obviously, an igneous rock. Gabbro, also. These are basically igneous rocks. The most common here would be the granites and the basalts. Sedimentary. With our rocks locally here, they're pretty good. In the Birds Hill area, Stonewall area, we have fairly good aggregates, but there are some aggregates in sedimentary you do not want, and these are highlighted in red. Clay stones, siltstones, shales. Shales are very undesirable. They absorb lots of water, and they pop. If they pop, you can have a deterioration of the concrete surface. Chert, it's also too soft of an aggregate. Low density aggregates, these you don't want. The conglomerates, sandstones, the carbonates are okay. So for sedimentary rocks, you have to be careful, depending on where your source is. Here locally, we've got a pretty good source. And we've tested those aggregates enough throughout the last 40, 50 years to know that we have good aggregates. Marbles, metamorphic rocks, marbles, slates, schist, gneiss, okay? You may have rocks, obviously, or particles in our aggregates that are metamorphic, okay? Normal weight aggregates, okay, this is what we're looking at. We're designing concrete for normal weight concrete. If you were going to do a heavyweight concrete, you may be doing it to design concrete for radiation shielding. You may be using hematite. You may be using aggregates that have a lot of metals in them. You want real dense, heavyweight concrete for radiation shielding. But we're designing structurally here in Winnipeg, and the pavements are typically normal weight concrete produced with normal weight aggregates. And you can see that when you produce concrete, you're going to have a range roughly of 2,200 to 2,400 for density. The old Imperial is 140 to 150. I may take it out. Don't worry, you don't have to know what it is in Imperial. We're metric now. I started, we all worked in Imperial, but that was many years ago. Okay. Again, lightweight aggregates. You may use concrete that you may want more as a fire retardant, maybe on a roof. You don't need any structural, say, capacity to it. So you can design lightweight concrete. with lightweight aggregates. These aggregates you do not want in normal weight concrete because they're not for a structural. You can have a structural as long as it's very low, but not for our normal weight. Like I said, you may have a concrete roof on a metal network, an open web joist, and that concrete roof may just be a fire barrier. Okay. So again, we don't look at these, but there is standards if in case you're using. So it's not for normal weight concrete. Oh. Yeah, here's the lightweight. Some of these stones, vermiculite, is a type of an aggregate that was used in a lot of insulations back in the 60s and 70s. They used it as home insulation. Okay, perlite pumice. Some of you may have seen those pumice stones for washing hands, to take off grease and so forth. And again, you can use lightweight concrete as an insulating concrete. And you can see here they're very lightweight. Don't worry. Heavyweights. This is the ones if you're going to do, say, radiation shielding. There's your hematite, iron. You may actually throw steel shot into your aggregate mix. So, okay. Okay, there's lots of properties. Don't worry, there's a lot of them here, and we don't look at all of them, but we're going to be looking at some of them throughout our design process. But typically, there's specification and limits, criteria for physical properties of aggregates, and there's tests that have been developed to determine those properties. Gradations, we know that, okay? A grading spec, whether you're following ASTM for asphalt or you're following a CSA grading specification. There's abrasion tests. So again, a characteristic of abrasion and degradation. We want aggregates that are durable, that will not abrade. Freeze-thaw resistance. Okay, if we have aggregates that are very high in absorption, they take on water, and then they freeze. And if they're weak aggregates, water expands when it freezes up to, I think, 10 times, if I'm not mistaken, or 9 times, and it'll pop. Sulfate resistance. Anybody know what sulfate resistance is? Anybody? Has anybody worked in construction where you were putting, say, piles in Winnipeg? You're casting piles into the ground or caissons? Anybody? No, nobody worked in construction? It is related not so much to a corrosion, Margot, but it is to an attack. Yeah, I guess you could say. Yeah, I apologize. Yeah, a sulfate attack, sulfate corrosion. Okay. Yeah, our Winnipeg soils here locally and in the Red River Valley are very, very, very high in sulfate concentrations. And soluble sulfate in soil can attack normal Portland concrete. And our normal Portland concrete that we're going to use in the pavements is classified as GU, general use. A few years back, it was type 10. The states still use type 1, type 2, type 3. We go to different designations, and when we're talking about cement, you'll see the 6 designations. But sulfates can attack normal Portland GU cement and deteriorate it. So anything below grade, piles, grade beams that are buried in our high lacustrine clay soils automatically use HS cement, high sulfate cement. So in other words, if you were building a house or you were pouring piles for a building, let's say you're working on as a project coordinator, concrete's coming to the job site, casting piles, caissons, whatever the case may be. If the contractor orders the concrete, he may have forgotten to say, I need a mix with HS cement. But the ready-mix producers are so knowledgeable now in the Winnipeg area, it's just standard. Anything below grade, they'll say, okay, it's an HS mix. So in other words, there's 6 different types of cement that you would use depending on what you're designing. Our pavements is general use, above grade, GU. Anything below grade, HS. And our levels can fluctuate from season to season, even across the construction site. You may be in one area where the sulfate levels aren't as extreme as in another. But Winnipeg is classified as very extreme concentrations of sulfates. So again, one of the tests you might test is actually in the soil, is to determine sulfate levels. Particle shape and surface texture. Talk about that. Grading, you guys know. Okay, even bulk density. There's the CSA 10A that you guys were just working on as we speak, lab 1. Okay, relative density and absorption. We need the density to be able to do our volume calculations. Moisture content. You're well familiar with how to do our moisture contents. That was one of the first things I think you learned with Natalie. We're going to look at some compressive and flexural strengths. Typically, if we had a lab where you would be in car seat, we would design a mix. We would be batching it. You would be making test cylinders for compression, and you'd be making beam specimens for flexural strength. And we would then, at 7 days and 28 days after casting those specimens, we would go back to car seat. We would do a compressive strength on your mix and a flexural strength on your mix. The only bad thing now is that the group that made the weakest mix has to buy beer for everybody. We lose out on that. See? Oh well, not much we can do about that, I guess. Anyhow. So yeah, so we're going to be missing that, but I'm going to be uploading, I'll be trying to find, yeah, nice, Kelly. I'm going to try and find YouTube videos that get into the compressive and flexural strength. And also, our lab assistant, he's using the ET TV group at Red River College. And we're looking at possibly doing a video on the compressive and flexural strength. Even though we're not there, we've got specimens there from previous years that we can test. So you can actually physically see a compressive and flexural strength and how it's done, and some of the requirements that you need to know about the specimens to be able to determine stress. Okay, like the diameter of the cylinder, you have to know, because you got to determine the cross-sectional area. When you load a cylinder in a compression machine, you're applying a load to a cross-sectional area. To determine the stress, you got to take the load divided by the cross-sectional area. So you have to measure these cylinders and so forth. Okay, so these are a lot of the tests that can be done. Alkali reactivity. Some aggregates are very heavy with alkali, and they will react with the cement paste. And they will produce deterioration. So you can have a physical attack. Alkali reactivity, whether it's ASR or ACR. Okay. Sampling. Any questions so far? I'm going quickly through this because there's a lot here, but I want to just look at the key points. And like I mentioned, the audio will have a little bit of a rendition for every slide. Sampling, okay? Sampling is just as important, if not more important, than the actual test in the lab. Because if you don't sample properly in the field, your results could be misleading, and the aggregate could be actually very good aggregate. Your test may show it's out of spec. So again, you have to sample properly, and Natalie covered that last year. Whether you're sampling off a conveyor belt, from the stream, dropping down, from a stockpile, from the gravel haulers, whatever the case may be, okay? Nominal maximum aggregate size. Okay. Maximum size is maximum. If I say your aggregate has a maximum size of 28 millimeters, that's it, maximum. 100% has to pass 28, okay? Now we're looking at nominal maximum size, 20 millimeter, okay. What that means is you can have 100% passing, or typically you're going to have 5 to maybe 15% oversize. So in other words, you'll see limits 100% passing 28 millimeter, 95% to 100% passing the 20 millimeter. That's the nominal size. You can have 5% oversize. So when we're talking nominal maximum size, it means that you can have aggregates sitting on that 20 millimeter screen. Okay, so you will look at some definitions right away exactly. So for our concrete here in the city of Winnipeg, the mix uses a maximum nominal size of 20 millimeters. Okay, I'm not referring to 19. Throw those ASTM sieves out the door. We're going to be looking at them when we're doing asphalt, because asphalt is still ASTM. Concrete is CSA. These are the sizes of the samples that should come in from the field into the lab. Grading, okay, we know you use 5 to 7 coarse sieves for coarse aggregate and about 8, roughly for the fine aggregate. And there's the range of particle sizes. You can see that if you sieved a 20 millimeter nominal size aggregate, you would get a breakdown all the way down to your 150. 160, I should say, and then 0.08. Okay. Here it is, maximum size. It's the smallest sieve that all of the aggregate must pass. Okay? Maximum 28 is maximum 28. 100%. You can't not have anything sitting under 28. Nominal maximum size, it's a standard sieve, immediately smaller than the smallest through which all of the aggregate must pass. So what it really means is it's the sieve immediately smaller than the maximum sieve, which would be the 28. Okay, so you got 20 millimeter. You have 95 to 100%. And again, you can have anywhere from 5 to 15% retained, depending on the specifications, whether it's an MI spec or City Winnipeg spec or CSA spec. CSA will be looking at it in the lab portion. We're going to be looking at the specification grading limits for 20 to 5 millimeter coarse. And we're going to be looking at it for the fine aggregate, the sand. Any questions so far? This slide I want you guys to really pay attention to. It is important because these are a lot of the factors that aggregates affects the concrete. In other words, the aggregates that we want to use all have to have certain criteria pertaining to the workability of concrete. Can we pump the concrete? Okay, a lot of times we pump concrete, especially to the upper floors. If we don't use a crane and bucket, we may pump concrete. Nowadays, a lot of them are pumping concrete for residential home grade beams or mason walls for the simple reason it may be congested. Now that the lots are a lot smaller and you got houses close together, sometimes you can't get a vehicle, ready mix truck in, so we pump concrete. We have to look at economy, porosity, how porous, what's the absorption? Will those aggregates shrink when they dry out? Will they expand? So we've got to look at volume changes, strength. Aggregates have to have a certain degree of strength. And aggregates can affect the uniformity between batches. Okay, a lot of times you'll have a concrete coming along and it's pretty consistent. And all of a sudden you have a batch that is not consistent with the other ones. It may be wet. People right away assume, oh, high slump, oh, somebody added the water. Not necessarily. Okay, there's about 7 factors, 5 to 7 factors that can influence a slump change. Just the grading of the sand, the amount of the sand versus the amount of the stone. Something happened at the batch plant, okay? So in other words, aggregates affect the performance of concrete in many ways, so we have to consider that. Okay. Again, this is just for formwork construction. Don't worry about it. We won't do that. Here's the specifications. This is taken out of CSA. If you download, or you're working with the CSA, you're working with the CSA standards through the library. Okay. Hopefully, you guys can all access it and work with it. I think Rosemary would be. Sent an email as to how to get to the library if you're experiencing problems opening up CSA. One thing I noticed in the table of contents for CSA, they're missing tables. Instead of having a table in CSA put right into the area that they're talking about, they've grouped all the tables together, and there's 25 tables. And they're between the 2 standards. You got CSA 823.1, and then you would have tables, and then the manual would start for testing point 2. Well, in the table of content, you don't see that listed as tables, but they occur between pages 162 and 185, so you don't have to look too hard, okay? Make a note of that. The tables in the CSA standards are pages 162 to 185. And that's the actual pages, page number of the page, okay, not the one that's shown on top. And you'll see in chronological order from table 1 all the way to table 25. And we're going to be referring to those tables because when they talk about specifications for grading limits, they'll refer you to table 4 or table 3 or whatever. The fine limits, I don't know what table it is offhand, but will be referred to it. I think it's table 5, maybe. Anyhow, you'll see it. Taken out of CSA, we have 2 gradings, fine aggregate grading 1 and fine aggregate grading 2. For the city of Winnipeg, when we're designing the concrete pavement, we're going to be following FA1. This is the one that's most common. And you can see here that with these 2 aggregates, FA2 means it can be a little coarser. Again, for certain reasons. What's your concrete going to be designed for? Okay. If it's very coarse, maybe it doesn't require workability. That's key. You know, we can design concrete that's going to give you phenomenal strengths, but you may not be able to work with it. What good is concrete if you're doing a floor slab, okay? But you can't finish it. Can't trowel it. Sorry, you can't float it, and then you can't trowel it. Okay? So you're going to design a mix for a floor slab differently than you're going to design a mix for a column or a grade beam where there is no workability. Okay? You fill a grade beam, you consolidate it by vibrating it, you screed it off at the top of the forms, and you're done. There's nothing to finish. Try and finish a rink slab or a floor for a building or hospital, whatever the case may be, where you need some good finishing qualities. So again, we can design concrete to give us strength, but if you can't place it, what good is it? You have to look at these things. Here's the 20 to 5 millimeter nominal size. Okay, these are the actual grading limits. And when we look into the CSA specification, table 4, whatever it is, I'll find it here shortly, we will be using the grading limits for 20 to 5 nominal size. Because there's other ones. There's 14 to 5, which means the top size. Sometimes on a bridge deck, if you're going to have extremely amounts of reinforcing, congested, okay, all your rebars are so closely spaced, maybe a 20 to 5 top size won't fit. You can't get the aggregate in between the congestion of reinforcing. Not our pavements, but on a structural application. So you may have to go small size aggregate. So now the maximum nominal size is 14, which is approximately a ½ inch, okay? 3/4, ½ inch. So here you can see now that it's a lot finer because it's a top size is finer. So applications vary. What is that concrete going to be used for? This is just a big Gilson sieve shakers. Okay, that's why when we did sieve analysis last year with Natalie, you guys and my groups, we do not do a sieve analysis in accordance with CSA or ASTM standards as far as the minimum mass of aggregate. For sieve analysis with 20 millimeters, your sieve should be minimum 5,000 grams, 5 kgs, minimum. We have one of these sieve shakers in the back, as you're probably well aware of it. That's what all the independent labs use. We used to just take a 5-gallon pail, 20-liter pail of aggregate, dump it right in, do the whole sieve on it. Because we can with these large square sieves, okay? So this one here is just another grading. They're talking about a 25 millimeter. Okay, again, this should be changed because that's based on ASTM. But you get the idea what I'm referring to. Okay, so that's why it's important to make sure that we try and follow standards when we can. If we can't, we have to state why we can't. And we have to take that into consideration. Just a couple of grading limit plots. I've used Excel. And here you can see we have the grading limits from CSA for the 20 to 5 millimeter nominal size. So our coarse aggregate for CSA should fall in between. And for a fine aggregate, this is FA1. Okay, here. So when you're plotting aggregate gradations, I know in previous labs a lot of students would plot one gradation per grain size distribution sheet. Here you can plot 2, 3, 4 gradations. You're going to see when we're talking about asphalt, I plot sometimes 5 on one graph. I can see it all in one shot. I don't have to flip through pages. Here I'm plotting the coarse, and here I'm plotting the fine. And then when I decide to plot it, I'm going to have another legend here. Maybe it'll be dashed or dotted to show the actual grading limit. So these are the limits, okay? Okay. Any questions so far? Like I say, I'm going to go through pretty quick here, but again, we'll have to go back. We've got aggregates. We also have cement. We also have water, and we have admixtures. So in other words, we're going to make up a paste of cement and the fines from the aggregate. So in other words, I had mentioned earlier that we want a coating of aggregate around. In other words, you want that paste to coat each individual aggregate. And you want the aggregates clean for the simple reason you need good bond. If your aggregates are dirty and you haven't washed them, as you know from the wash sieve analysis, you can have deleterious material adhering to the aggregates so that when the cement paste tries to bond to it, it's a weak point. When you test concrete and you break that cylinder open, let's say, and you see that all those aggregates are split, have been sheared, you got a good concrete. That's what you want. You do not want pop-outs. In other words, when you test concrete, you don't want the failure around the aggregate. You want the failure through the aggregate. That's what's going to give you the strength. If you got pop-outs where you got an intact aggregate on one side of the fracture, and you can see the dimple or the crater where that aggregate was on the other side, it pulled out. Okay? The bond broke. You got weak concrete, especially if there's lots of that aggregate. Good concrete, you're going to get some pop-outs. That goes without saying. So always look at a failure plane. Now, with crushed aggregates that we're using, it's pretty hard to determine unless you quickly look at it right after the test. Did it fracture in the test, or was it fractured from the crushing operation? Okay, so you have to look at it and make some judgments there. If you're using aggregates, say, from the Burns Hill source, where you may have some crush, but most of it may be just natural erosion, subangular, somewhat rounded, and those aggregates are sheared from the test, then you know that the bond was greater than the tensile strength of that aggregate. So that's what you want. Now, how much cement paste is going to be dependent on the voids. Okay, the voids between the aggregates we're trying to fill. Now we can design a mix to really reduce those voids, but then you wouldn't have enough paste content to make it workable. So you want to reduce the void content, but not so much that you can't work with the concrete. So in other words, you're going to separate some of those aggregates, okay? Now, this is where the grading comes in. We all know that ball bearings, all the same size, will not compact very well. If you have a uniform grading, whether it's all coarse or all fine, you can only compact it so far. But if you have a well-graded material with a good distribution of aggregate from coarse all the way to fines, you'll fill those voids with the finer aggregates. If we reduce the void content, we'll have more of an economical mix. I mean, we can have large voids and just fill it with cement paste and water, but it's not very economical, and we're also looking at strength. The more voids you have, the less dense the concrete's going to be. So here, if we took 3 beakers, and here's a good analogy. If you took 3 beakers, and 2 beakers were filled with aggregate of uniform size, but different size, the void contents would be the same. If you filled it with water, okay, the left beaker and the center beaker, the volumes of those voids would be the same, regardless of whether this aggregate is larger than that. Now, if you took and mixed these two together, now you got these finer aggregates filling a lot of the voids. Your void content goes down by the water level. Okay, makes sense. So now, this is in red for a reason, because it's a very good true and false question. The amount of cement paste required for concrete is related to the void content of the coarse aggregates only. True or false? False. It's the combined aggregates. Okay? It's the combined aggregates. Because now the amount of cement that we need is going to be based on the voids in this third beaker here on the right, that is a mixture of well-graded aggregate, coarse and fines. Okay? Any questions so far? Here's mine. And here's the sketch. This is what we want to do. Okay? Particles are in contact. But like I said, we want to make sure that every aggregate is coated with cement and water and paste. So we're going to mark. The lower sketch represents a dispersal of aggregates. The greater amount of paste is necessarily greater than the void content in order to provide workability. Okay? So we're deliberately ensuring that we have good workable mix. If you don't have a certain amount of void, you're going to have a problem with that concrete. Okay? Maybe you're going to have a concrete in a column. You're going to vibrate it as you're going up the column, but there's nothing to finish other than the finish when you strip the forms off. You want to make sure you don't have voids, you don't have any bug holes. Okay? So the actual amount is influenced by the workability and the cohesiveness of the paste. Okay? Stick them together. Okay, the fineness modulus. Did Natalie explain to you guys last year why when we calculated a sieve analysis, we had percent retained and then we had cumulative percent retained, which you don't nearly need to calculate percent passing, right? It was just a good check to see, did you get back to 100% retained? Anybody? There's also another reason why we're doing it. I set up a lot of those sieve analysis forms for a simple reason. When I came from industry, we always did cumulative percent retained for the simple reason we tested lots of concrete aggregate. And there's a criteria called the fineness modulus. And we need to know that on the sand grading. You have to know the fineness modulus for sand because you're going to use that fineness modulus in the calculations of the amount of coarse aggregate and eventually how much fine aggregate you're going to need in a concrete mix. Okay, you have to know the FM, and it's an index. Okay, it's an index of the fineness of an aggregate. How fine does it run? Okay, now you're going to have an FM number. The higher the FM number means the coarser the aggregate. And CSA will have limits on it, and again, it'll be in one of the tables. But I'll tell you right now, write this down because we're going to need those limits when we're looking at our sieve analysis. It should be between 2.3 and 3.1, according to CSA A23.1. That is the fineness modulus. So in other words, all the suppliers' aggregates that are being used in the city of Winnipeg concrete mixes has to meet CSA criteria. And it has to be between 2.3 and 3.1. I think AMI has changed those limits a little bit for their mix, but we're not looking at an MI mix. We're going to be looking at a mix for the city of Winnipeg. Okay. So the FM of any shipment of aggregate made during the progress of the work should not vary by more than plus or minus 0.2. If the FM is an indication of how coarse that aggregate is, and that FM is all over the map, what does it tell you? That your grading is changing. It's telling you that your sand gradation is not consistent. If it's not consistent, it can affect performance of your mix. One of the reasons, you got a very stiff mix, the next load is very wet. One slumps, one pulls away. If the gradations change, it's going to affect your mix. So again, and it's very important in asphalt, you have to try and maintain those gradations as close to the gradation that you use for designing the concrete mix design. Concrete mix design is going to be based on a certain grading. the mix gets approved, you start batching, but your aggregates are all changing, well, now your mix design is not going to perform because the aggregates are not the same. You'll never get them exactly the same, but you're going to have a plus or minus tolerance, and the city of Winnipeg shows that. Okay, how's my time doing here? Okay, any questions so far? We're going to look at how to calculate the FM right away, and you'll see in the next slide here. Here it is. This is why we had accumulated percent retained. Okay, you can calculate percent mass by just 100 minus 2, 98 minus 13, 85 minus 20, 65 minus 20 gives you 45, 45 minus 20. Or 100 minus 0, 100 minus 2, 100 minus 15, 100 minus 35. This is why I've always liked to do cumulative percent retained, because I need to know this number. And for concrete sand, the FM is a summation of the cumulative percent retained. So 0 plus 2 plus 15 plus 35 plus 55 plus 79 plus 97, but does not include the 0.080 or the number 200. Does not include that. So it's just typically you add these up, you get 283, divide by 100, you got an FM of 2.83. Okay, it's an indication. And remember, the higher the number, the coarser the material. So you can look at the grading envelope, and if your sieve analysis is running very, very close to the bottom grading limit, it tells you what? Your aggregate's on the coarse side. If it's following close to the upper grading limit, the envelope, it's finer, right? It's running right down the middle, that's what you want. Okay, so this is how we have to calculate fineness modulus. And you'll need to look at that and calculate that. Our next lab that we'll be looking at here shortly, and is going to tell us from your gradation, you can actually calculate it without the sieve. We're going to be looking at only percent passing, okay? But if you look at the percent passing, you can automatically calculate the FM, because you would say 2 plus 15 plus 35 plus 55 plus 79 plus 97. I'm not looking down these columns. I'm subtracting this in my head from 100. If you subtract each one of these from 100, you're going to get cumulative percent retained. So when I give you a gradation, you should be able to calculate FM like nothing. Okay? You don't need to have this to calculate this. If you know this, you can calculate cumulative percent retained. Then you can also calculate individual percent retained. Okay? All it is math. Couple of graphs here. Have a look at them. This gives us an idea of the size of aggregate. Now, what we're looking at is we know now that certain sizes of aggregates is going to influence how much water we need. Now, we're going to be running out of time here shortly, and there's a lot of stuff I want to cover, but throughout your reading week, I don't think any of you guys are going to Mexico or anything, or something. Go through this, look at it. If you have any questions, I'm available, definitely. But we're looking at the water and cement demand based on aggregate size, and there's a correlation. Obviously, if we have aggregates that have a higher maximum nominal size, it's going to require less water than a finer aggregate size. Anybody know why? Why would a real fine mix of cement and aggregate require more water? Of course. Okay, let me say it this way. What has more surface area? Fine aggregate, okay? Look at the concrete sand, you look at the concrete sand, and then you're going to look at the coarse aggregate. Which has more surface area of particles? The sand or the coarse aggregate? Anybody? Fines. Exactly, Sean. So more surface area means you're going to need more cement and water to coat it. So the finer the mix, the more water and cement requires. Therefore, more groshi, more money, it's going to cost more. Cement's your most expensive ingredient. So if we can design a concrete with a larger aggregate, all the better. Like our like our pavements. Why are we using 20 millimeter? There's no reinforcing. We just got dowel assemblies. We could probably go with 56 millimeter aggregate. Like I mentioned earlier, last week, we had a problem with the porosity of the aggregate and decracking. The absorption rates on the aggregates, larger size aggregates, were great. So now we're faced with another dilemma. But if you had good aggregates and you didn't have decracking, in other words, those projects, if any of you guys worked for hydro projects up at Kiosk or Wasquatum or any of the other ones, you've got mass concrete going in. You're going to use the largest aggregate you can to reduce thermal expansion, okay? Less cement, less thermal expansion. And thermal cracking, thermal problems in mass concrete are a problem. So here you can see a lot of things coming into play. So if we look at the aggregate versus the cement and water, you can look at this graph, and we have what's called air and train concrete and non-air and train concrete. Does anybody know what the difference is? What's air and train concrete versus non-air and train concrete? Anybody? You can blur it out instead of having to type it. Come on, you guys. All of you guys that tested concrete should know all this. Nobody did concrete testing?
Would that be when they use like a vibrator to remove the air bubbles from inside the concrete?
No, that's entrapped air or void. You want to, yes, consolidate it. You can over consolidate it or over vibrate and knock out some of the air. But you've got concrete that has voids. Okay, and these voids are filled with the paste. But you also want microscopic small air bubbles in there. And that's called air and train concrete. Non-air and train concrete just means it'll have those microscopic air bubbles, but very little. Now, why are we introducing air and train concrete versus non-air and train? Why? Right, Mitchell, for when it freezes. Air and train concrete is used in areas, it improves workability too, but air and train concrete is in our climate to reduce or almost trying to eliminate freeze-thaw damage, okay? Concrete absorbs water, and as that water freezes, it expands, creating tensile forces. If we introduce a network of microscopic and small air bubbles, they're like relief ports. As the water expands, the tensile stresses are stopped by a bubble, okay? Then water again from one bubble to the next bubble. The water within the mix is going to travel. It's going to freeze, it's going to expand. Bubble's going to stop the amount of expansion. So what you're trying to do is eliminate spalling or scaling. And a lot of times you'll see our pavements where they're peeling at the very top. It's just a thin layer. It's scab is just kind of peeling off. It's scaling. A lot of that is freeze-thaw damage. And we have that in winter. You know, when your curb or your pavement in this sun right now, it's cold. But it's sunny. You may get some heat buildup. And at night, it freezes. Thaws during the day, it freezes. So you got various freeze-thaw cycles. So concrete in our climate that's exposed to the elements outside has to be air and train. Non-air and train concrete, an interior floor slab, your basement floor slab in your house, you don't need air and train concrete. Now, air entrainment does help workability. So even a lot of designers will always design air and train concrete, even for interior applications where you don't have freeze thaw, because it helps to improve. And also from a design point of view, cement. So here, if we look at it, you can see non-air and train concrete and air and train concrete. But the thing that we're looking at here, and learn how to read these graphs because I do put these out on quizzes and I tell you, show me the relationship. What does this graph show? Well, here you can see that as the maximum nominal size of aggregate increases. Now, again, these are taking out a lot of the PCA manuals, so they're using ASTM. So they're using the ASTM sieves instead of our Canadian metric. But we can quickly bounce back and forth. 4.75 is a 5 millimeter. 9.5 is 10. Here's a 14. Here's a 20. Here's a 28. Here's a 40. But anyways, if we look at the ASTM, you can see here that is the maximum nominal size of aggregate increases, the water demand decreases. If the water demand decreases, and we're going to be talking about what we call a water cement ratio. There's a certain ratio we need between water and the amount of cement we need for strength. That'll also decrease. More economics, less cement. Okay? Now, they've done testing. They use a slump with approximately 75 millimeters. They had a water cement ratio of 0.54. So this graph, this is the control. And you can see here that it doesn't matter whether it's non-air entrained or air entrained. As the nominal maximum size increases, the water demand decreases. Okay? You can see the imperial here on the sides. So just, there's a good criteria here. The other relationship is that you can see that air entrained concrete needs less water at a certain magnitude. Let's take our neon 19 millimeter or 20 millimeter, and if we go straight up, you can see that if you're designing an air entrained mix, okay, it needs less water than a non-air entrained. If it uses less water and you're going to maintain the water cement ratio at 0.54, you're going to use less cement. Bingo. Okay. Now, there is the admixture cost, air entrainment, but it would be relatively small. So here you can see the benefits of an air entrained mix. In our climate, for a real important factor is to resist freeze-thaw damage, but it's also a benefit for us from a placement and workability point of view and cost. Okay, so here there's two relationships. Okay, so learn how to read these graphs. Okay, this is a combined grading, but instead of plotting percent passing, you can see they plotted percent retained. Don't worry about this too much. It's a different way of reading it. A lot of suppliers read this because this tells you how much of each size you have. Whereas typically when we're looking at percent passing, we're looking at how much percent of the total aggregate passes a certain size. This is retained, okay? These come in handy when you're looking at tarantula curves. Anyhow, we don't get into that. So this is just a different way of plotting a gradation. Instead of plotting percent passing, we're plotting percent retained. Okay? Abrasion resistance, a couple of tests that you do here. LA abrasion test. I'm not going to go through it. And some of the limits the CSA has. Okay? Again, when you're testing that aggregate for abrasion, it has to have a certain amount of loss, a certain amount of wear. CSA has limits for that. Soundness. This is going to simulate freeze-thaw. Okay? Alternate wetting and drying and temperature changes. It's called the soundness test. And this is where you actually soak aggregate in a magnesium sulfate solution over 5 days. Okay? You soak it, you dry it, you soak it, you dry it, you soak it, you dry it, you soak it, you dry it. Then you're going to sieve it. And magnesium sulfate is going to react as an attack, a chemical attack, if you want to call it, the aggregates. Will those aggregates resist the cycling of freezing and thawing? It's called the soundness test. Okay. Again, there's CSA tests for all of these. So if you went into A23.2, you went through all the testings. The A's are the aggregates, the B's are the cements, and C's are, yeah, there's A's, B's, and C's. But anyway, they all have a designation. You'll find the soundness under the aggregates. Again, there's certain criteria, certain limits. Okay, aggregates are unsound when the volume changes. Okay, we're using that magnesium sulfate to soak up the solution, and when you dry it, it shrinks back and forth. Okay, volume changes. That's what we're trying to simulate. The effects may be local scaling, some of our scaling of aggregates, extensive surface cracking, or disintegration over considerable depth. Okay, spalling scaling. Soundness of aggregates. Again, that's tell you how to do the test. I wouldn't tell you. Those are the limits by CSA. Okay. Don't worry, you don't have to know those, but they're there if you're running a test. Okay. Let's just let's go till 10:15. We'll take a break. and then we'll continue into the lab. Particle shape, irregular shapes, they all have a bearing on the performance of the mix. So you can see here, it's been naturally worn, rounded, probably a river gravel. You may have taken it below the water table. Okay, angular, has sharp edges, you can see, crushed, part of the crushing operation. When you're processing aggregates, you may have been processing Bird's Hill source, but there's large boulders, and when the boulders are crushed down and cobbles are crushed down to size as you're processing aggregates, you're going to get a mixture of crushed and semi-round. Flaky, laminated, these are very critical. You don't want too much of them. Okay, there's a maximum width to thickness ratio. Again, I don't ask you to learn these ratios, but just understand the different type of aggregates there are. Elongated. Remember I mentioned basalt, one of the igneous rocks. And many years ago, one of the bridge engineers for the city of Winnipeg wanted to make a maintenance-free bridge deck. Well, in our climate, I was on drugs or something. Can't. But anyways, he decided to go with basalt. It's a real hard, dense aggregate. However, you're processing it, it gets very elongated. It's just a molecular makeup of the aggregates. Almost like slivers. Okay? And what was happening is when they were testing that concrete, they were getting pretty low breaks. They couldn't understand it because they're using hard, dense aggregates, clean, good mix. But what was happening is when they looked into the investigation and they looked at the break of those cylinders, there was usually a shear plane along the aggregate length. So what was happening is as they're rotting the cylinders, the aggregates would all go into vertical orientation. They'd all flip up. So now it's almost like needles in the mix instead of cubical. You want a cubical aggregate, okay, where the width, the height, and the depth or breadth is the same. Cubical. It's a cube, okay? That's what you want. You don't want flat, platey-like, or elongated where the ratio between length to width is too great because you're going to get different shear characteristics on that aggregate. Remember, we're shearing aggregates. That's what gives us our strength, not how much cement you have in it. You can have as much cement as you want, but if your aggregates are garbage, your mix is garbage, okay? Key. So again, we have to look at the shape of the aggregate in relationship to the ratio between the three dimensions, okay? Thickness, breadth, whatever you want to call it, okay? And here you can see some large pictures. Okay, now here's something, we'll stop right here. Crushed aggregates. Some agencies ask for a minimum crush count. I know MI did, okay? When you have a rough texture, aggregate that's rough in texture, what's going to have better bond between the cement paste and the aggregates? A rounded, semi-smooth aggregate, say cubical, or a cubical aggregate that has sharp, angular edges and a rough surface. What's going to give you better bond between the paste and the aggregate? Which one? Anybody? The rough one. Exactly. But who cares? It's important, but when is it important? Okay? Rounded aggregates suitable in concrete as flaky and elongated particles reduce workability, increase water demand, and reduce strength. Okay? So we don't want flaky and elongated. Now, with angular particles, the bond between aggregate particles is higher due to interlocking. Okay? Plus, when you have a rough texture, you have better bond. However, because now you got peaks and valleys, you got more surface area on a crushed aggregate than if you took one aggregate that was subangular, semi-round, whatever, and somewhat smooth. You don't have enough peaks and valleys in the surface of the aggregate. Okay, so a crushed one's going to have more surface area, which is going to need more paste, which means it's going to need more water, which means it's going to need more cement. Money just went up. Okay, to make it workable, like if you're using 100% crushed for a floor slab, remember, you got to finish that floor. You got to power trowel it. You have to finish it by hand, And then power trowel it. You want something that's workable. So you're going to want a workable mix. With crushed aggregates, you don't get that workability. You can, boom, throw in more cement paste. Money just went up. Okay? For strength, they'll give you the strength equal. You can design a 30 MPa, 32 MPa mix. Okay? Now, if you're going to keep the water cement ratio the same, and you've got crushed aggregates, you're going to need to increase the cement and water demand. You can still maintain the same water cement ratio, but now the crushed aggregate is giving you more money. It's going to cost you more money because you're using more materials. Bond is very important in the flexural application. Okay, compression, not so much. But there's not much difference. So in other words, however, due to the higher surface area, angular particles increase water demand to maintain workability. As a result, the same cement content and same workability, the rounded aggregates give higher strength. Okay? Keep that in mind. Okay. Surface texture affects the bond to the cement paste and influences the water demand of the mix. So smooth, the bond between the cement paste and aggregate is weak. And when we say weak, it's weak relative to the crushed. It's not weak where it won't give you your strength because you designed for that. You got clean aggregates, you'll get bond. Rough, bond between cement paste and aggregate is strong. Surface texture is not a very important property from a compressive strength point of view. But aggregates with rough surface textures perform better under flexural and tensile stresses. And our pavements are inflexural. But our pavements are not high-strength concrete. You don't need the crushed aggregates to meet a 32 MPa mix. Nowadays, if you cannot design a 32 MPa mix minimum, say to meet the city of Winnipeg pavement criteria, get out of the business. You got no right being in the ready-mix business. It's not rocket science. There's more important factors than strength that are more critical. Abrasion resistance, durability, freeze-thaw resistance. Get my drift? Okay? So strength is not key. I mean, it's key, don't get me wrong. Sorry, let me back that up. It's required, it's important. Very important from a structural, for columns and grade beams, and if you're doing a structural building, yes. But it is not high-strength concrete. When I was in the precast industry, I was designing a mix at one time just to see how high of a mix we can design. And I was up close to 90 MPa. Okay, that's pretty high strengths. And we sort of had that between our plants across Canada. Okay, good. And there's again some smooth and some rough. Okay, moisture conditions. We'll leave it here because we're going to have to get into the lab component. It's now 10:13. Let's take a 15-minute break. We'll get into the labs. This moisture conditioning is important because remember when we were talking about specific gravities, you calculated oven dry, you calculated SSD, and you're now looking at calculating the apparent also. And these are the moisture conditions for each of the related to specific gravities that we'll be looking at. So again, the lab will be due Friday. It doesn't have to be due today unless you want to. You can submit it today if it's done. I will never say no to accepting something done ahead of due date. But again, because of the week coming up, and we've done some lab changes, some groups have changed. I'm trying to reduce the number of groups. Anyhow, we'll talk about those lab groups after the break here. So is there anything on here that we've covered? If you review those PowerPoint audio that I have uploaded, you should be okay. If my audio is not very good and you can't get something, just send me an email. I'm here, guys. Okay? Let's take a break. If there's no other questions, we'll take a break. I'll just pause the recording, but we'll come back. You don't have to log back in. Just stay open on your screen and you'll be okay. Any questions? Okay, I'll stop sharing and I'll pause the recording. And we'll see you here at 10:30. Dominic? Good. Okay. Okay, we're back, hey? Everybody grab a coffee already? Good. Okay. Lab 2, sieve analysis. You guys done numerous sieve analysis, so we're not actually going to do a sieve analysis, but we're going to analyze a typical sieve for coarse aggregate and fine aggregates. And we're going to look into it, and then we're going to say, well, okay, we're batching concrete, we're doing concrete mix design. So much coarse aggregate and so much fine aggregate is going to get blended, obviously, because there's going to be a certain amount of each. Now, this blended gradation has to meet a certain criteria. Okay, it may meet their own respective sieve analysis, but based on the blend, it may throw it out from what the city wants. The city has actually specified a mix grading of what the concrete aggregate that's in the mix should meet if you looked at the coarse and fine mixed together. So we can determine that a couple of ways. One is basically theoretically. We just have a gradation of the coarse, we know the gradation of the fines, and we blend it. Is it a 60-40 mix? 60 coarse, 40 fine aggregate, or 65-35, or 55-45, okay, or 58-42, whatever. So we have to play around with it. Now you realize that I'm talking more aggregates than fines because that's what we want. For our pavements, okay, City of Winnipeg has a slip form mix or a hand placed mix. You'll notice that a lot of the big streets, a lot of big roads, and even with MI, they use slip form pavers. In other words, the concrete is extruded out of the paver and it's going to stand up by itself. It's consolidated, it's vibrated. So automatically you know that the slump of the concrete, how much is going to slump? It can't. It's going to be a stiff mix. Smaller jobs where they're going to be placing the concrete right out of the back of the truck. They're going to put it in between the forms. They're going to have probably a power screed, and they're going to screed it. And they're going to finish it. So there's handwork involved. The city allows a hand placed mix to have a higher slump. In other words, it's going to be more fluid, easier for them to work. Okay, so we're going to look at the mix design, and we're looking at our aggregates. We want to make sure that these aggregates meet the City of Winnipeg spec. And the City of Winnipeg in the specification has it. Oh, recording. Yep, sorry guys. Thank you very much. Okay. Good. I didn't get into real big specifics, but okay. Thank you very much. Sorry about that. Anyhow, we're back to recording. Okay. So you've got it in Learn, a link to the City of Winnipeg Standard Construction Specifications. So I'm going to pull up their spec here and we're going to look at it. And look at what the mix design has to meet. In other words, what properties does a concrete mix have to meet? And we're going to look at it from a point of view from the aggregates first. Okay. So you guys can all see this? Good. I'll put my chat back in here. And we're here. This is the 3310 City of Winnipeg, revision 17. It's their latest one, December 2015. We used to always purchase these standards from the city, but now with internet and being online, every time there's a revision to a certain spec, it gets uploaded. So you can always have the most recent standard specification. So if you go on that link, it will always give you the latest one. And here on this one, they've highlighted areas that were revised. So again, it's quite intensive. We're going to look at the design requirements. So we're going to look at section 6. Prior to that, we're going to look at the materials also, just briefly. So this is a typical standard spec. MI has one, and it's for concrete pavements. Okay. So you're talking about aggregates, and there's a frequency of testing that the ready-mix producer has to do on his aggregates should he want to supply concrete to a contractor on a City of Winnipeg project. So you can see that there's lots of tests that he has to test every year on his aggregates. If he uses the same source, okay, and has been approved, but they still want certain tests done every year to ensure that they're consistent. Some tests are 2 years, both for coarse and for fine aggregates. Okay, now here's the combined aggregate gradation. Okay, we're going to look at individual gradations of each, and then when it's mixed design, tells you that you need a 60-40 blend. If you take 60% of the coarse, 40% of the fine aggregate, mix it together, is the gradation going to meet these limits? Okay, this is a combined. Now we're not looking at type 2, which is Portland cement sidewalks. We're looking at pavements, okay? So we're looking at these here. Okay. Type 1, all Portland cement concrete except for sidewalks. Okay. And you can see here that there's the grading limits. It has to meet. Coarse have their own individual, the fine have their own individual, blend them together. Now this blended gradation is not a CSA criteria because MI might have a different one. City of Brandon may have a different one yet. That's why the CSA are set up with individuals. Your mixed design is going to dictate. Here. Now, first of all, we're going to look to see if we can meet this grading by coming up with a combination. We may find later on that when we do the mixed design, let's say we determine 60-40, we may find out later on that the mixed design tells you it's going to be end up 58-42. Then we look at it again. Now at a 58-42, are we still in spec? Okay. So here, I would suggest you download, so you don't always have to go onto the internet, download this specification. You're allowed to do it, okay? So here's the grading we're going to try and meet. And they talk about supplementary cementing materials. They talk about the water use. So you can see that they're talking about a lot of information here about all the materials. Okay, they're talking about a coarseness factor of the aggregates between 45 and 60, and we'll look into that. Okay, so we're looking at it from a cement point of view. Later on, when we look at the concrete mix design here, you're going to find out what we actually have to design for. Okay, here. Come back to that. Concrete supply, ready-mix concrete production facilities, paving equipment. There's specifications on the equipment and on the plant. Concrete finishing, concrete curing, weather conditions, quality assurance, testing frequency, and so forth, okay? Basis of payment. How are they going to get paid? Come on. Okay. The next one is, what does the mix design have to meet? Okay. Now, this is what's called a mix design statement. It's not a mixed design, it's a mix design statement. The owner says, this is what I want. I want a concrete that's going to give me this strength. It's going to give me this air content criteria. It's going to give me this slump. It's going to be exposed to these kind of conditions. And from that, the ready mix producer designs a concrete mix to meet those criteria. So here we're looking at a type 1 paving mix. Okay? Concrete pavements, commercial approaches, curb and gutters, monolithic curb, and sidewalks. And we want the concrete pavement. Okay? Now, we're looking at two types of type 1. Slip form paving and for hand placement. We basically design for hand placement because when you go back to car seat and you're actually physically mixing this concrete, we want one that's not too stiff for you guys to make cylinders, to make flexural beams, to do slump tests, because you're physically going to batch the concrete, dump it into a wheelbarrow, and then you're going to play around with it. So we've always designed for a concrete pavement, but a hand place mix. As you can see here, they're talking about slump criteria. The amount that's going to slump. Slip form paving for hand placement. So we're going to look at hand placement. Okay, keep that in mind. So here we can see that there's some criteria. The class of exposure is C2. We'll look into CSA as to what is C2. Okay, it's a type of exposure that your concrete is going to be exposed to. So then that governs certain criteria: how much cement, how much water. Okay, they want a minimum 32 MPa. That's minimum. That's not what we're designing for. What we're going to be designing for is based on a water cement ratio. You have a water cement ratio down here, maximum water cementitious ratio. They call it cementitious on the fact that now we no longer only use cements. We'll add fly ash, we'll add some pozzolans, we may use silica fume. So the term now is cementitious because most mixes nowadays are made up of not just straight cement. They have supplementary cementing materials. Predominantly City of Winnipeg fly ash, okay? Which is a byproduct from the coal burning industry. And we'll understand that when we get into fly ashes. Okay? So here's the criteria that our mix has to meet. We're going to design for a slump of 20 plus or minus 20 millimeters. Okay? That's plus or minus, essentially 50 to 90. That's going to tell us how much water we need. Obviously, if the slump is higher, you're going to need more water because you want to make it more workable. Remember, slump is not, some people says it's a test to determine workability. It's not. The slump test measures consistency. Okay? I can have two 75 millimeter slumps and they'll be different in workability. They'll be different in workability. So how can you say it's a measure of workability? It's not. It's a measure of consistency. If you've got 10 loads arriving at the job site and every load has a 75 millimeter slump, it's consistent. If you get 10 loads and you have an 80 millimeter slump and a 120 millimeter slump, and then you're back to 90, and then you're back to 80, and then you're back to 120, and you're 100, and you're 95, that's inconsistent. That's all it measures. It's a sign of measuring consistency. Does not tell you how much water is in the mix. Because remember, slump can be affected by sand grading. So how do you know it's water? How do you know the driver stopped and added water? Okay? Capiche? Okay. Our aggregates are 20 millimeter. That's kind of standard now here in Manitoba. And air content, 5 to 8%. Remember, we're placing air and trained concrete because it's subjected to the freeze thaw. It's outdoors. And now we're going to add an admixture to make sure we have 5% to 8% of that cubic meter of concrete has to be air. So you can see we're designing a mix on volume. We're going to need to know how much water, how much cement, how much coarse aggregate, how much fine aggregate, how much air and training admixture to give us 5 to 8%. And if we design with fly ash, also with fly ash. Okay, so now we're looking at all individual ingredients. We put them together and we make concrete. So we're looking at this spec. So refer to this one quite a bit. Class of exposure, okay, and the maximum water cementitious ratio. Now, you'll know that with a 0.45 water cement ratio, you'll be probably closer to the 40s as far as MPa. It says minimum 32 MPa, it does not say maximum. So this is what governs, okay? Your maximum water cement ratio is essentially what governs. You may have, like I say, you maybe 40 MPa in here. So be it. It's based on the class of exposure. What's our concrete subjected to? Our pavements are subjected to freeze-thaw, chlorides. Remember, we use de-icing chemicals with our salt when we add it on the streets for, to get rid of ice. So our concrete is exposed to the attack of salts. And more so, the salt basically attacks the reinforcing, which expands because of corrosion, pops concrete. Not so much salt attacking the concrete. Okay? So type 2 would be, again, a different spec. But we're not working with type 2. We're working with type 1. Okay? Concrete pavements. Okay? And it gives you certain criteria. Sometimes we want to open the pavements up early. Contractor places a pavement slab Friday, and the business owner is all upset because it may take him longer to. He says, "No, I got to have traffic back on Monday, 2 days basically, Saturday, Sunday." So he's going to want higher strengths so he can develop an early strength quicker. Concrete gains strength over time, okay? And we get about 2/3 to 70% within the first 7 days of casting concrete. That's why we test concrete at 7 days typically, and then at 28 days, because we know that if we test concrete at 7 days and we know what the strength is, we can make a fairly accurate prediction that, yeah, we'll have no problems at 28 days. Concrete is designed to meet strength at 28 days. Typically, it's achieved a lot earlier. Okay, but it's at 28 days. So we're going to come back to this. I want to get into the sieve analysis. So we're going to look at our aggregates here. Any questions on this? Always refer to this specification because we're going to be referring to it quite a bit. Because we have the combined grading from here, and we're going to need to know those parameters for the concrete mix when we're designing a concrete mix. Okay? I'm going to go to another one here. Okay. These have been uploaded and learned. This is the gradation that, say, you would have determined had we had a physical lab. And again, because these lab groups are going to change a little bit, I'm now having some groups of 4, and I will give an updated, right after this meeting, I'm going to give an updated lab roster. So if your group changes for lab 2, it changes. Lab 1, you can work with your original group, or if you've made a switch already, that's fine. But we're going to basically have 6 groups in group 1 and 6 groups in group 2. And there's really no reason why I split them as group 1 and group 2. This is stemmed from when we used to batch concrete. I would split my 18 students into groups of 9 and groups of 9. And when you're batching concrete, you don't want to have all 18 students batching one load. Okay, you'll be stepping over everybody. So we split them. Okay, 9 and 9. That's why I made one ABC average. But in our case right now, don't worry about this average. You know your group number. I will give you the revised one. Most of them won't change, but some will. You look at your group number, and that's the grading. So here we're looking at fine concrete aggregate. Okay, so there's the nominal size, 100%. Sorry, passing the maximum. This is the maximum. The nominal size is 5 millimeter. Maximum would be 10. So here's the grading limit. So group 1A did a sieve analysis, group 1B and 1C and so forth. And that's what you would physically do had we had the lab. So you're going to look at this, and so you pick your own group. Okay. Now, when I get your labs for your specific gravities, we will pencil them in after. Right now for the gradation, we don't quite need it, but we'll need the specific gravity that you've now determined in lab 1, and we'll put them in here. So now, whether you're group 1A or 1B, calculate the FM. Remember, we just covered that. So, okay, this is 2 plus 11, okay, plus 22, plus 53, plus 85, plus 94 will give you your FM. All I was doing is I was doing cumulative percent retained. You just subtract each one of these from 100. Okay? Piece of cake. And the other reason is I like using cumulative percent retained. regardless of whether I'm calculating the FM or not, is I can subtract the number from 100 in my head quicker. I don't have to punch all these numbers into the calculator when I'm doing sieve analysis. Once I calculate percent retained, I can calculate cumulative percent retained, and then bingo, I can calculate percent passing. Okay? So here's the CSA grading limits for fine aggregate, FA1. And we'll go to CSA here right away, you'll see it. So these are the grading limits. So if I go into the CSA standards, I refer to tables. Okay, I'll pull these out. Now, this is from the table 10. I have my tables mixed up, but the fine grading limits, you'll see is in CSA standard. And let's see. Whoop. Just trying to get the, and you'll find it on page, come on, 173, okay? You can see it, okay. So we're going to use FA1, and on our spreadsheet, I already had placed those down. Read the footnotes, okay? They talk about the FM here. Remember I said 2.3 to 3.1? Also, there's a, what do you call it, a little cross here to signify a footnote. These can increase up to 5%, minus 200, provided that if you did a hydrometer analysis on it, the minus 200 only had less than 1% clay. Okay, remember, we know that these are silt and clays. Minus 200 can be silt and clays. So you can increase this to 5%, provided that if you did a hydrometer analysis, you prove that of that reading you had less than clay, then you can go less than 1% clay, you're okay. Okay? So footnotes are always an important part of a table. So this is table 10, grading limits for fine aggregate. If we go to the next table, we're looking at the coarse aggregates. And here's the grading limits, remember? We had them even in the slides. 100, 85 to 100, 50 to 90, 25. And this is for 20 to 5. You can see that there's different ranges. We used to, in the city of Winnipeg, before we went metric, we would have 20 to 5, and we would blend it to get 40 to 5. We had two aggregates. Okay? Any questions so far? No? So this is the one we're using. There's your grading limits there. I can't highlight them because CSA won't allow that. Can't do anything with CSA, just read it. They've locked everything out. Okay? So these are the grading limits. Table 10 and table 11, part of A23. So we looked at the fine aggregate. Now, if you do the coarse aggregate, same thing. You take your group number, and there's your coarse aggregate with the minus 200, okay? Again, once you've calculated your specific gravities, and absorption will include them. For coarse aggregate, we don't need the FM. You need them for fine aggregate. You need the FM because we're going to use that FM value to figure out how much coarse we need. And you're also going to use the bulk density of the coarse aggregate that you've done or are doing right now. And we'll put these in. Then we'll have this sieve analysis, we'll have absorptions, we'll have specific gravities, and then we can design our mix based on volumes. Any questions so far? Oh, when did Winnipeg go metric? They went 1977, I believe. Tim? Yeah, you're close. No, it would be later 70s. I believe it was 77. Because I remember having a CSA standard manual. And I remember the 77, I think, went metric. Okay, I could be wrong by a year, but I think it's 77. So we're metric now. Okay, we're not imperial. The US, I think, are the only ones around the world that are still imperial. And there's so much information out there. And even this manual here, the integrated manual, it's in your references. This is such a good one here. And because it's American publications, a lot of it refers to imperial, but they do give the metric. So this is an excellent manual for research, references, talks everything. Talks about curing, talks about placement, talks about cracking, shatter slabs. So just look at the Table of contents here. Let me quickly find it. Peter Taylor, I heard him speak in San Antonio when I was at a conference. Just an excellent, excellent guy. He's been with the. So there it is. There's all your chapters. Basics concrete. We talk about basics of concrete pavement design. Okay, thickness design. Consideration factors to accommodate for design. Water. We talk about aggregates, which is what we're talking about. We're talking about dowel bars. We'll be looking at some of them. Hydration, transformation of concrete from plastic to solid. Chapter 6, mixture design and proportioning. Some of this we'll be looking at, you'll be familiar with when we're going through it. Okay? So anyhow, when you get a chance, take a look at it. If you got trouble sleeping, start reading it. Guarantee you'll be sleeping in no time. Okay? So we're going to go back to our nations here. Okay? Now, what does this all mean? Okay, I'm going to put up another slide here, and I thought I had it up in here already, which I don't, but I will. Give me a minute. I'm going to see if I can pull it out. Can everybody see this? Yes, no? Coarse and fine concrete aggregate gradations? Yes, okay. I'll blow it up here a little more. Now, I've set up a spreadsheet here for you guys. You have to do your own calculations because this isn't PDF, but say group 1A, whatever. You're going to include the gradation from the coarse spreadsheet and the fine spreadsheets in here. And then you're going to have a percent. Now, did Natalie go over with you guys about blending using those great blending charts that MI used to have? Okay, when you guys did aggregate combinations, you guys used what do you call it? Sort of a graph to pick out. Is that correct? Yes. Now, that's a good way of doing it, but it takes forever. Nowadays, with Excel spreadsheets, and most people just use an Excel spreadsheet. They put their formulas in and they can calculate it. So this is what you have on Learn. And I'm going to pull up something else here right away, and we're going to go through a couple examples just for the heck of it to see how it's going on. So give me a minute here, and I'll pull up my. Okay, where the heck am I here? Okay, just give me a minute.
Hey, that big integrated concrete design manual, is that available for download off Learn or?
Well, there's a link. Yeah, it's on Learn. There's no restrictions. You can download it because it's a government production from the States. Most government research proceedings have no restrictions, so there's no copyright. So you can either purchase them, download them. Most of them are free, so they're downloaded. So if you go onto that link, you'll find it, and then you can download it and save it to wherever you want. It should be under the reference documents in the concrete. It'll probably be under the lecture part, not underneath the labs. Does that answer it?
Found it.
You found it? Okay. Okay, I think I'm just gonna. Can you guys see the spreadsheet here? Am I sharing it or not? Or you still have the original one? Sharing two here, it tells me. Just give me a minute here, guys. I think okay, let me just. Okay. Everybody see this? Group 1A, 1C example? Yeah?
Yep.
Okay. Now, this is just an example, and I've got two of them beside here, but you're only going to do, if you're group 1A, you're only going to play around with 1A, and that's how I set it up. But anyways, here's the coarse grading that we had. Here's the fine grading. So let's look at 1A. Don't worry about 1C right now. Okay? These are the original gradings. Now, remember, we typically want more coarse than fine aggregate. Are they going to meet specs? Here's the City of Winnipeg combined grading spec here. You can see on the right-hand side, 190 to 175 to 95 and so forth. So in other words, when I take my coarse aggregate, my fine aggregate, and I blend at 60-40, it's got to meet those specs. Well, let's try 60-40. So what I've done on my spreadsheet is I can just put in the values, and you see it changes. A lot quicker than what Natalie went through with you by using those grading charts, combined aggregate, two aggregate combinations. Right now with Excel, boom. And all this is here is if I take 60% of my percent passing, okay, for the course aggregate, I get 60. 60 times 100 is 60. 60 times 92 is 55. 60 times 60 is 36. 60 times 27 is 16. Here's my fine aggregate. Now you have to put the hundreds in here above it because it's doing mathematics, okay? So if I took 40%, 40 times 100 is 40, 40 times 100 is 40, 40 times 100 is so forth. 40% times 98 is 39%. So now you add these two together and you get a blended gradation. Now, does this blended gradation, does it fall in between here? Does it meet these spec limits? Sorry. Does it meet these spec limits? Well, you can play around and look at it, but I always just plot them. There it is. Okay. Now, right now I'm showing both the 1A and the 1C, but let's just look at the 1A, which is the blue line here. So you can see that if I blended 60-40, my blue is coming out of spec here because this red is a grading envelope for the City of Winnipeg. Okay. So you can see I've also got two fine here on the 1 millimeter and 2 millimeter sizes roughly. Okay. These are my grading limits taken from the grading limit chart. Okay. So I can see I got to play around with it a little bit. So I come back here now. Let's try 62 and let's try what, 38? That should give me 100, right? Hey, let's look at the picture. A little bit better. I brought the fines in. My course might still be out. Now, keep in mind, the City of Winnipeg might say, well, don't want it. Your aggregates have got to be in spec. Just because your aggregate's out of spec, it doesn't mean you can't make good concrete. Okay? You may have to do some tweaking. Like I said, strength is the last of our worries. Typically, strength isn't a problem. But sometimes if the aggregates are too coarse or too fine, it's going to affect workability. Okay? We're looking at pavements and placement. You're going to look at a power screed, and you're going to look at, the big derbies, bull floats. Shouldn't be a problem. If our slump is between 70 plus or minus 20, we should be able to place that concrete and finish it. Our aggregates may be out of spec a bit, but maybe the concrete industry has to do what the asphalt industry does. Those of you that have worked with asphalt, I've blended sometimes 5 aggregates for asphalt to make a blended mix. In fact, on one job, they contracted to bring in an extra bin to his plant because there was a 5-bin mix instead of a 4-bin mix. Typically with asphalt, the province here, or City of Winnipeg, you'll have 4 aggregate types. We'll use 4 different aggregates to blend that to get the aggregate gradation. Here, we're only using 2, the coarse and the fine. So if the coarse is out to lunch and the fine is out to lunch, You can blend all you want. You may not get it in spec. Would the client accept that? Maybe. If you can show to him that this mix produces good concrete, so what? Aggregate's out. But somebody say, no, spec is a spec. I want it in. Well, he's the owner. You did the job. Okay? So now we can say, well, let me try, I don't know. Let's just play around with that. Let's go 70-30. Okay? And this is what the beauty of using an Excel spreadsheet. Instead of using those charts where you, with Natalie, where you were using a 2 aggregate blend and you plotted it and then you drew your line. Now you can see here, we're looking at the blue that's gone out quite a bit. It's very coarse here now on the 10 millimeters. Okay, it's gotten still out a little bit here on the 14. Okay, and also out here on the 5. So you can see now. So what I want you guys to do for next week is you take your individual gradations, okay, put them on a spreadsheet, do it manually, I don't care, and come up with a combined grading. Try and get it into that spec as close as you can. You may not be able to. So, and instead of having a letter report with it, I want you guys to figure out your blend combination, and you can do footnotes on the bottom of your spreadsheet. Mention the fact that if your aggregate doesn't meet spec, it doesn't meet spec, okay? Because again, many times we deviate from a standard, but we have to note where we deviate. And same with this. We might state that the aggregate does not meet the grading requirements specified by clause such and such City of Winnipeg specification CW 3310-R17. However, the anomalies or the deviation is minor, and it would appear that concrete shall be designed successfully to meet the other criteria. Okay, so this here is an analysis. I don't necessarily want a letter report like we did for, I'm just trying to minimize your work. Typically, I would ask for a letter report on this analysis, but this is more number crunching, okay? It's more calculations. They're important. I want to see how you've calculated them. And I think most of you are pretty proficient in Excel. You'll see also here what's called the coarseness factor. In the City of Winnipeg, I believe, if you remember the spec, I think it was 45 to 65. Can't remember. But we determine it. It's the cumulative percent retained on the 10 millimeter. Okay, remember, these are percent passing. Okay, so cumulative percent retained. So here, you can see from my, I brought it in from another spreadsheet, but it's 100 minus 27 will tell me that I've got 73% retained. Divided by the cumulative percent retained on the 2.5, okay, I've got 2% passing. That means I must have 98% cumulative percent retained. So just a division, and I get a coarseness factor of 71. If it's 45 to 65, I believe that's what the City of Winnipeg spec stated, it doesn't meet. But, so play around with those numbers. I mean, I only put 1C here just for comparison, but you're only going to have 1A is going to have basically this, plus the spec, And here you with 1C, if you look at 1C, it almost looks like it might be a little bit better. See, the grading for 1C looks like it's better grading. You got to play around with here because you're a little bit on the coarse end. Okay, you're running back down on the bottom here. If your sieve runs along the bottom envelope, it's coarse. If it runs closer to the top, then it's on the finer side, right? Because this is percent passing. And again, you put a title on your graph, Pavement Mix Design Group 1A, Combined Gradations of Concrete Aggregates. So again, I insist that you have a title, have your group number, because, for example, if I didn't have my group number here, and I found this graph laying on the floor, whose is it? Where did it come from? Okay? Put a title on it. concrete coarse combined gradations of concrete aggregates. If you were plotting just the fine aggregates, you'd say gradation of fine concrete aggregate. Okay. Any questions on this here? Let me look at the chat. Sorry, I cleared it. Okay. Any questions on here? So right after this, I got a call coming in at 11:30 for a meeting. But anyways, I will revise the lab group. Most of them won't change. There's some of them. There won't be a group 1G, okay, because there's going to be only, I think it's 6 and 5. But anyhow, I'm going to put up a revised lab group roster. Check that one out to make sure you have your right lab group. For lab 1, if your lab group changed and you're in a group of 3 and you're now a group of 4, fine. Lab 1 can be submitted with the old group, or if you made the switch before, I was in discussion with some, if you made the switch before the due date, which is the 12th, and your lab 1 is going to be with your new group, all the better, okay? Any questions? This is important from the fact that we have to know, you might find out later, let's say we're going with a 60-40 mix. And when you do the mix design and you base it on the FM of the aggregate sand, and you base it on the bulk density of the coarse aggregate, and you find out that your mix design actually comes up with a 58-42 coarse to fine aggregate ratio, then you plug this back in here and say, okay, my mix design, as far as the proportions of coarse to fine, is that. Then you will check it and say, yeah, hey, I'm still in spec. Okay, that's what it's going to be. So we're starting off as initial. We know that we want to be more coarse. I mean, 50-50, okay, let's say we start off with 50-50. Let's say, let's start off with 50-50. Where am I going to be? Well, you can see you're way out to lunch. Obviously, you got way too much fines. And again, if you're in a floor slab, you may have a mix for a floor slab where you may have almost a 50-50. You may have 55-45. Because now you're looking for workability. You're looking for a fatty concrete mix that's very putty, easy to finish, okay? Pavements are a little different. You're using different screeding operations. You're using vibrators and finishing, okay? So that's kind of where you can start. If you don't even know where to start, you can say, I'll go 50-50. Oh, obviously I got too much fines, so I'm gonna go 55-45. Let's see what I'm looking here. It's getting better. You can also look at here, okay? You've got obviously 100, 96 you're in, 78 you're in, 60 you just make it, 47 you're in, 41 you're out, 35 you're out, 21 you're just out, 7 you're in, 3 you're in, and 200 you're in, or 0.08 you're in. So again, you can look at the chart, or you can look at your limits here. When is Lab 2 due? Well, Lab 2 will be then due. You've got, and I'll put that in the Dropbox. Lab 2 will be due on the 23rd then, because you've got reading weeks next week, right? Yeah, you got that, Timothy, right after reading week, 23rd. Okay. Again, if you have any questions, any concerns, I suggest first work it among your groups. That's why you're working in groups. Okay? Lean on one another. Help one another out. That's what it is. That's what you're going to be in business. You're going to be out there in the workforce. You're going to be working in groups. You may be putting proposals together. Okay, you may be bidding a job together where you're doing estimates together. You got deadlines to meet. So I will help you. But work among your groups. It's a group effort, remember, okay? Not only from the reporting. I would suggest you calculate maybe yourself and then compare your answers. Because I've just been marking some final exams from my structural group. And I know that in their labs, some of them said they were part of the lab group and that they contributed, but they couldn't calculate a sieve analysis. So they never did it. They never did the assignment. They never did the lab. If you can't calculate a sieve analysis, that tells me you haven't done it. You may get rusty by not doing it, but I'll come back to you. It's like riding a bike. Or if you couldn't calculate a hydrometer, you didn't do it. Because I had exams handed in with hydrometer worth 12 marks. They got a 0 on it because they couldn't fill it in. So go through the calculations. It's the only way you're going to learn it. Okay? And here you can see that when I changed to 55-45, the coarseness factor came down to 68. Okay. Any questions so far? Use the CSA standards for tables. If you want to read some good reference material, that manual, ICMP, whatever it's called. Okay. Anything else? Anybody got any questions? No? So again, your group, lab group 1 test data, lab group 2 test data, you'll find what's what. By hopefully, I should try and, I should get the lab revised group up within an hour or so. You'll have it before mid-afternoon, and you'll know what group you're in. Chances are, if your group hasn't changed, you're the same. It's just that the 1G will no longer be around now. Okay. If there's nothing else, it's clear as mud. You're free to go. Have a good rest of the week. Have a good reading week. Work hard. Keep safe. And again, I'm available. And even on weekends. Like I say, sometimes on weekends I don't quite get to the computer, but I've been busy marking now, so I'm basically been working most weekends. Okay. There's nothing else. Have a good one, guys. You're welcome, guys. You're welcome, Cole. Are you referring to about the lab 1 calculations for specific gravity and density? Is that what you're referring to do or die? Yes. No, we don't. I remember last year Natalie probably insisted that you give a typical example. With the formulas given and your answers are totally wrong, then I know you probably didn't plug in the right value. There's no need for it. Okay. If you calculated everything, your calculations are correct, then you obviously know what you're doing. All you're doing is you're just repeating a formula. Okay. The lab 2, again, if you're going to do a spreadsheet manual, I will double check those calculations. So no, you don't have to give me an example. All I know is that you're taking 65% of the initial grading, and then you're taking 35% of the initial grading of the fine, and you get it combined. If your numbers are correct, then you obviously know what you're doing. Okay. Yeah. No point reinventing the wheel. Now, if you copy it off somebody, that'll show up in your exam or your quiz. If you copied and didn't do the calculations, I'll know by you failing the quiz. Okay. And you got any other questions? You're welcome there, Du. Welcome, Marcos.